Okay. So today I'm going to be going over some of the VHDL for state machines. You've started getting familiar with it with that lab. And then I'm going to go over some more state machine example. Well, there's one more example. And then I'll hand back the exam and we'll kind of talk about that. First, did I point out while we were in the class in lab, I forget if I remembered, I posted an announcement that is just a copy and paste from a job posting on LinkedIn. What that is about this time of the semester, I like to show you guys like where you're going and what you need to know. I would recommend going and looking over that one. And it talks about, you need to know VHDL, you need to know C++, which you'll learn in embedded systems. You need to know DSP, which we have a course called DSP, right? And so you can kind of see how these courses start to tie in together and where they're going to get you like an actual job. And what stood out to me with that one is it was asking for 2 years of experience is all, and offering $115,000 a year. So we've already been kind of noticing an increase in pay because we have more and more tech companies coming to Utah, and it's hard to recruit to Utah. So being in Utah, you're kind of high on their list for wanting to hire because they want people that are going to stay, right? So that's the kind of job. It's a good example of something that you could, after this class 3610, go and start hunting for like a very similar internship. So what I want you guys to put into context is that we're not teaching you kind of arbitrary stuff. It does apply to specific jobs that you're going to get. All right. So state machines. If you recall this figure, right? The first thing we need to do is remember where we are. What is our current state? This is just a register, right? It's clocked. Then we need some way of determining what is our next state. And we call this our next state decoder. And all that does is it's combinational logic that feeds into the current state and takes inputs, some I, from outside of the system, and where we are now, right? It makes a decision based on where are we and what's the command, what's happening next, what's the input. Then we need to send out information, and we do that using an output decoder that, depending if you're a Moore state machine, cares only about the current state. If it's a Mealy state machine, it cares about the current state and the input. All right. So we started with that lab. I kind of directed you through the easiest way to make a state machine in VHDL. Let's go with a bit of a harder one that deconstructs into all three parts. Let's use all three different parts, and we'll start with the next state decoder, right? So the next state decoder is going to be in a process. And again, it's combinational logic. So if I'm using a process and want to stay in combinational logic, I just take all of the possible inputs and add them to the sensitivity list. So if I add I and however many bits of current state, right? That basically makes this combination because it will react anytime any of those inputs change. Then we go to the heart of our state machine, with is a case statement, right? And we always case on where are we now? What is our current state? Now, current state, remember, we want to create a signal for current state. And we could do this with like a standard logic vector or even bits, but it's easiest to use what we call the enumerated type, right? Just like we have the type for standard logic vectors, we have types for bits, we have types for, what we're going to do is we're going to create an enumerated type. So type, I'm going to just call it state type. I think is And then we just list all possible options for this, right? So in this case, we would have something like a state machine as A, B, and C. Let me just, this one. And I'm going to build up, the example that I'm going to use for this is going to be what we call a sequence detector. So a sequence detector starts in some state and it waits to see whatever the first bit of that sequence is. So let's say I want to detect 101 in some stream of data. So we have I that is updating each clock cycle, and I want to assert a true statement if I see 101. Now I'm going to do this as a more state machine, so I'll actually add a D state. Okay, so A, B, C, D. So that's just saying this state type is A, B, C, or D. Now, when you do this, it's really assigning numbers to that. And you can dive in and actually figure out how it assigned its state. There is some optimization that goes into this, like we talked about in our last lecture, right? Where there are some rules of thumb that it tries to assign the numbers. And you can kind of learn more about that if you want. In our book, there's a section on state optimization. That's a little outside of the scope of a freshman level class, so we're not doing it. But that's what it's doing, is you're basically just creating a string of constants, right? When you declare a constant, you say constant A is 0, 0. But it's doing all that rest of the work for you. That's what this enumerated type is doing. But this is just having a type. You don't have any signals that you can work with yet. So you do need to declare signal next state, current state of type state type. This is a mistake that a lot of people make, is that they try and use the state type as the state variable, but it's not, it's a type. So don't confuse that, it happens a lot. All right, so now I've made the signal current state, and it can be A, B, C, or D. That's the only things that it can be. If I do something else, it'll throw an error. All right, then I say something like, when we're in A, what is the next state logic doing in A? Well, let's go to how we design state machines. I have A, B, C, D. I'm looking for 101. Well, if I see a 0, I haven't seen the beginning of that pattern. If I see a 1, though, I go to state B. So this is just an if statement. If, and I'm going to pretend like I is a bit so that I don't have to do a bunch of equals. So if I, then my next state gets assigned to B. Else, next state stays in A. Now we have to be careful, because the issue is when we have this assignment, if we don't remember this else, this isn't like software where it doesn't update if I don't write it, right? In software, I could just hide this and say if I is equal to next, if I, then next state updates to B. Otherwise, it won't change. But in digital logic, technically what's happening is else don't care. If you don't write the else's, otherwise don't care. Most of the time it will do what you think. It'll just keep the same value. Sometimes it doesn't, and it can be really awful to debug. So in VHDL, generally speaking, it's best to enumerate all options, meaning end with an else. All right, that's all. When B. Well, B, I'm looking for 101. So if I see a 0, I get to move on. Okay. If I don't, if I saw a 1, Does that work? Is that where I want to be? What we're missing though is if I see a 1, let's look at this pattern. Right? So I've seen a 1, I go here. I see another 1, I go back. No, I don't. I want to be ready for that 0, which is here. So it's actually 1. Because this is I saw a 1, and this is I saw 1, 1. Okay, if I see a 0, and now here, 1. Right? And now my state detect is where I'm going to have detect, and my output is 1. Because it's a more state machine, I have to be in a state to do it. Okay, so the same thing, if I see a 0, well, this was 1, 0, 0. Well, that's a reset. You failed. You didn't detect it. And then D, we've detected it. Regardless, 1 or 0, we're going to come back to A next. All right. So that B then, right? B just says if not I, next state is C. Else, right? And then we just fill this out for each state, right? And this is what's nice with these state diagrams, is it makes it really easy to turn them from a state diagram to a case statement for the next state logic. This is why we like state diagrams, is as long as you drew this correct, it's really hard to mess up this. All right, I'm not going to finish it. That's our next state decoder. Now, well, current state is just a register. It's not doing any real thinking, but we need to update that register, right? Because what's happening is each time I see a rising edge of a clock, is I'm taking whatever the output of this next state is, this NS, and I'm loading it into current state so that it can be fed back around. Well, that's easy. We just say process on clock let me do it this way. Current state equals next state. Done. That's the register, right? Because each rising, oh, almost forgot. If RE on clock, right? Because otherwise I've messed up, and we'll do it on both the rising and falling edge. So there we go. Clock happens. If it's the rising edge, we take whatever the next state output is, throw it on here. Current state has updated, which means this process will update, right? Because if this changes, this runs. If this didn't change, if the next state stayed the same, right? We're in B, next state is B, this process won't even run because current state didn't change unless I does, right? That's how the VHDL is working. Well, there's nothing more complicated than that to the there. Now the output decoder, it only cares about the current state because I said I'm making a more state machine, right? So the output decoder is, well, there's an end process here. There's an end process here. So outside of any processes, I'm going to stick to strictly combinational that just says my output, let's call it F, just for ease. We just go ahead and say F gets assigned to 1 when current state equals D, else 0. right? I haven't detected it unless I'm in state D. This is strictly combinational logic. Now, I'm a big fan of the output decoder being strictly combinational. So you can, however, mix and match the, let me zoom out on this one. You can mix and match combinations of next state and current state decoder, or the current state and output decoder, right? You can combine these guys into sections of blocks, sections of code in there. So let's look at the process for the next state logic. It is easy to combine the next state logic with the current state. And in fact, this is what I encouraged you to do without being very so explicit about it, is in the lab, is because it's really easy in that we don't even need the next state logic if all we do is process on the clock and say things like current state. All right. Now, you have to make sure that the input I is synchronized to this state machine, right? So you don't want to have the I changing at the same time as a rising edge. But other than that potential issue, what happens is, let's say we start up. We start into state A. And to make sure that happens, we write some sort of, so here I need the if rising edge of clock. But I could, if I want to make sure I start into A, the good way to do that is do the clock and reset, right? And do an asynchronous reset, right? This says if reset equals 1, state equals A, else if rising edge of clock, case, right? That's a good way to make sure you know where you're starting in the state machine. Now, I'm in state A, a rising edge of a clock happens. And it says, oh, I'm in A, I is true, let's change current state to B. But since current state isn't in this process list and I need the rising edge, current state has updated, but I'm not there yet, right? So current state updates to B, but on the next rising edge of the clock, I'm in this case statement. It doesn't like instantly change anything going on here, it just prepares it. Now, this is really good and easy to use. I like it as designed. The one trick is that you can be in a situation when your timing diagram, your waveform in your simulation will show your current state as B. And let's say that I had some output decoder in here, which I'll get to in a bit, that says F equals 1. Well, what could happen is on this rising edge of the clock, I update my current state to B, but F isn't 1, right? Because I'm not in this case yet. I will be when the next rising edge of the clock happens, but I'm not there yet. So be aware, that's the one downside to this method. All right, other than that, I no longer need next state logic. Signal, right? It's a little bit simpler, a little bit cleaner. I really like doing this. Now, the next thing that we can do is we can bring the output decoder into this case as well. So that the only thing we have going on is process. Well, that's a little bit weird. It can have a benefit because, again, if you imagine when we're in case C, if the output decoder is strictly combinational, current state updates as soon as the rising edge of clock goes into C, potentially, right, depending how you program it. And so our output goes 1 and we go to D, and your, how do I describe this? Probably graphically. clock out. Okay, so this clock happens, I'm in C. But it has decided that if I get a 1, I'm going to D. So my next state, as far as it's concerned, is D. So output goes high, right? And now I go into D, and D evaluates and goes, oh, well, my next state is A, so I'm dropping. So even though I'm in D, my current state, because of the if statement, is A, right? So this is actually off by a little bit as well. So be aware of that synchronization issue. It is possible. It's also possible to avoid this depending how you program it. And an easy way is to combine the output decoder into the process, and you just do that by saying, into here, you just say F is 0. Right? Done. Now is 0. Now you have to be careful that you enumerate this output for all states. Don't leave 0 here and then assume that because, well, I was in A and I have to be in A before I go to B, right? Well, if I was in A, it was 0, and I come to B, I would assume that it's still 0. But the trick is that technically it's don't care. It will probably work until it doesn't, which is, again, really frustrating. So if you do this, just make sure that you list all of your outputs in all of the cases. Okay. Well,
I have a question.
Yeah.
So if you state that F is equal to 0 at the beginning of your when statement, but then your if or else statements change F later, say like if not I, F would be, just for example, if not I, F is 1, else it stays the same.
yes.
So in your if statement, you would say F is 1, but in your else statement, do you need to restate that F is still 0, or can you leave that as well?
I will actually get to that because that's a good question. Because literally what I was coming up to next. So here works if you're outside of the if statement. If you're putting them in the if statement, you would do this sometimes because that's how you change it from a more state machine to a mealy, right? Is because if it's in the if statement, now it depends on the output, depends on the input, not just the current state. So what you're suggesting turns it into a mealy machine. And so it's something you might actually do. If you were to do that, instead of putting any at outside of the A, you would put all of your outputs inside both the if and the else. Now, I don't like doing that because these if else statements can get like if this, else if this, else if this, else if this, right? And they can get really long and it gets really tedious. That's why I'm a big fan of the output decoder being its own thing, as combinational logic. Really big fan of it. You can actually change the output decoder to have a process and a clock on it. If you want to change the, right, if you want to delay this by 1, you can just have the flip-flop to that. But yeah, so you would have to copy and paste your outputs a whole bunch to make that work. Again, it would probably work if you didn't do that, but it's not something that I want to gamble on at all. Okay, so I did all this. This is what it would look like if you're cramming all of the logic into one block. You can combine them how you want. Going forward, I recommend here, what I want to point out next is with the sequence decoder. So a sequence decoder is actually really common in state machines, and it's a really common homework assignment. I'll certainly give you one coming up this week. The way that I suggest making them, if I want to detect 101, is start by making the path that you know is what you want, right? And if it's a mealy machine instead of a more state machine, I'm actually just going to erase this code. I think you're okay here. Remember how I said in general, more state machines take more states? Well, that's just because I can do 1, 0. I do, this is output of 0, this is output of 0, and this is 1 with an output of 1. It is also 0 with an output of 0. And then this guy, right, same thing, 0, 1. I don't need the D state because I don't need a state specifically to assert my output. All right. Well, let's go back and look at a problem that I've kind of intentionally built into the more version. Let's say that I have the input string now. There's 2 different ways that I could detect this. Is the question, the way I'll ask it is, do I want to detect overlapping sequences, right? Because I have this 1, 0, 1 that I definitely want to detect. But do I want to detect this one as well? Maybe, maybe not. So if I say detect 1, 0, 1 with overlapping sequences, means this. So how do we do that in the more state machine? Well, it's just we change D is all. That's the only thing we have to change. So let's think about it. We go ahead and we write the sequence that we want to detect first. So I would write the 1, 0, 1. Right? I know that's what I want. Now, I want to make sure, so I've got that detection. I want to make sure that I get a detection here. So if I see this 0, where do I need to go to make sure that I can detect this one? I'm in D, right? 1, 0, 1. Back to C. Because this is saying I've seen a 1, 0, right? That's what state C is telling us, is I've seen 1, 0. And then it flows back. Whereas if I see a 1, where do I go? I don't even go back to A if I'm here, right? Because if I see a 1, then I've seen 1, 1. So the only way I end up back at 0 is if I'm in C and see a 0. Which is saying if I see 2 zeros in a row, I go back. Right? And a really good thing to do in these sequence detectors is to, when you're done, first go back and find these examples, the overlapping, and make sure they work. 1, 0, 1, 0, 1. And then you can do a similar test case. 1, right? That test case, the non-overlapping, which is 1, 0, 1, 1, 0, 1. Make sure that we don't miss some of those. And then you may want to go and do some test cases that are like 1, 0, 1, 0, 0. Where do we go? 1, 0, 1, 0, 0. So that's sequence detectors. Is in general, draw the path that you know you need. Draw the right path first. And so when I ask you on the exam to go detect for me some pattern, you'll at least get most of the points if you just draw the arrows for the actual thing. Then you can go back and fill in the alternates. Make sense? Okay, good. Did anyone here not make it to the lab? So everyone was here in the lab for this Monday, I guess yesterday. Wow. Okay, so I won't cover too much of that. If you're watching online and you need help on the lab after this, I think it should be kind of obvious, hopefully. Reach out, email me. I have office hours. Zoom is really good for working with VHDL help stuff. And for project 2, right? So on Thursday, my plan is I'll send out an announcement when I make sure that I can get it, but I plan on meeting in lab so that you guys have an extra hour and a half to spend working on the project with me around. Because project 2 is important. And then we'll move on to project 3 shortly. Okay, so the next thing on my list is exams. Braden. Gavin. Right,
There
no, dude, that guy. That makes you Bryce. Not get your name. I will do it someday. Oh, you did yours online. I don't think I've graded this yet. I will get that. David. You're, I don't know, Brian or Bryce.
Right.
You can have my solution and you'll like whatever. Oh, you've got a copy. Okay. That's good because I may have. All right. Overall, I was happy on this exam. You guys did really well. The average was in the mid, like 83, something like that overall. A little bit lower than the last exam, but that's fine. The last exam, if you recall, it was out of 106 points on the first exam. And then when I put it into Canvas, I left it out of 100. So there was a 6-point curve on the first exam anyways. And I was going to go back and fix it, but I'm just going to leave that here to kind of make up for this exam. The curve ends up working out the same way regardless. Overall, this first page was done really well. Only a couple people missed the true and false. Nobody forgot to do it, which is good. Number 7, I'm still learning to write questions, I guess. So if I messed up and marked you down, if you wrote either a D flip-flop or a T flip-flop, let me know. Because initially what I wanted was clock divider, right? But you're not wrong, right? Because a T flip-flop is really easy to use to reduce the speed of a clock. So I shouldn't have marked you down for that. If you were the first person or second person I graded, maybe I made a mistake. So just double check that on number 7. So a lot of people put T flip-flop, totally fine. Number 8, the reset is synchronous because it's inside of the if statement and the rising edge of clock. B on that one, the 2 devices are a MUX, which is the one that I definitely wanted you to get. The other one, I had mentioned in class, but we really hadn't talked a lot about it, and it was in the lab, is just an output enabled buffer. Like that. I accepted a lot of things. If you just said buffer, that was okay. Tri-state buffer is okay. There's a couple other ones that were okay to write. So that's what I was looking for. C, it is a MUX or output buffer is combinational. There's a possible mistake I made in grading. If you wrote D flip-flop and then said sequential, right? Because I refer back to part B, you should be right on that. As long as the combinational sequential matches what you wrote in part B, you should get the points for that one. Part E, this one was about half the class missed, and there were a couple of reasons. Why did I create the QS signal instead of just assigning Q to D? An acceptable reason is because my Q is an output, and to do it the other way, I would have had to put my output on the right side of the equation. Another one is because I wanted that output enabled. right? I wanted to be able to turn on that output enable. Number 9 was just straight out of the notes, like I promised I would have some questions like that, right? Where I said, what is the right way to gate a clock? And the bad way is the AND gate that almost everybody got. Now, the right way, a lot of people remembered that it was something to do with a mux, but they forgot how to do it. Right, where what happens is if I'm not enabled, when the rising edge of the clock happens, I just take the previous value. And if I am enabled, then I pass I in. That's the right way. This is the one that a lot of people missed. Maybe a third of the class. Okay. Number 10 is JK flip-flop. I disguised it by putting duck and goose instead of J and K, but it should be obvious, I would hope, because there's no other flip-flops that are that complex, right? Flip-flops are really simple devices. So number 11, D flip-flop. Number 12, write a component declaration for an n-bit adder. So there were a couple of things that I was testing on this. Number 1, I was testing that you knew what a component declaration was, because a lot of people keep screwing this up. And that's just saying where you say component, give it the name, and then fill out the port, right? I saw a couple of people that did instantiations instead. And then I wanted to make sure that you remembered if I'm doing a variable bit, you use the generic map. I didn't care if you wrote a value there or not, as long as you had the n colon integer or n colon standard logic, right? Something that showed me that you had that generic map. And understood that's where you were going, what you would need. Then the third component of this is in the port maps. I wanted you to make sure that when you did the n-bit adder, the vector sizes were n-1 down to 0. Now the output port, you could n down to 0 or n-1 down to 0. Either is correct. I didn't mark down for that one, but for the input ports, I needed n-1 down to 0. The timing diagram, you guys rocked this one. So it looks like the timing diagrams are starting to make sense to most people. I think the only mistake that I saw, which is very frustrating, by the way, is on the lines A, B, and C, you weren't counting up, right? So instead of doing right, so this row should be 0, 1, 2, 3, and so that means I go every other one, right? 1, 2, 1, 2, and so on. That it's 1, 2, 3, 4. And the count up wasn't there, so I ended up with weird things that was like 0, 1, 2, 3, 7, 6, 3 again. I don't know. It makes it really hard to grade. So number 12 was just a really simplified address drawing. And it was just testing to make sure you remembered what an address decoder did, right? So, well, I was testing 2 things. The address decoder, when I give it an address, 0, 1, 2, 3, I have to send an activation signal to one of these and only one of those. So they were horizontal. So this row was the one that had what I was looking for, which was 0, 1, 0, 1. And the big trick on that is I said it was gray coded binary. So 1, 1. Right, if I'm gray coded, 1. About half the class got missed the break code. Not quite half the class, more than half of them got it right. Number 15. I'm really happy with you guys, actually. This was supposed to be the hard question, so I always do like a bunch of, couple of easy, couple of medium, and then like one hard question. This one you guys did way better than I thought you would, so congratulations. This timing diagram is hard. And what it comes down to is that I have these two JK flip-flops. This JK is connected straight across. Oh, really, it's Q and Q bar, right? It's going into J and K. But then this one crosses them over. If they didn't cross over, it would be kind of a boring system, right? But that flip means that all of your inputs are always opposite of each other, right? So I'm always doing a set or reset action. I'm never doing a toggle action, right? We're never doing a hold action for that JK flip-flop. And moreover, it takes 2 clock cycles for it to take place, because this transition is just straight across. It just holds. So you end up with I'll make sure I do this one right. So this is J1, K1, this is J0, K0. So for the signal that's going into J1, which is also Q0, so I labeled those to help make sure that we didn't get confused on what was what. I said both Q0 and Q1 start at 0, right? So they're I'll do Q0. It starts at 0, triggers it to 1, and then this clock cycle happens, and then this clock cycle happens, and it's the second clock cycle that causes it to flip again. Q naught, so K1 is just the opposite of this, and then the output on Q1, which J0 is the opposite of the Q1, is the same thing, except for that it starts low and toggles high at this point. And it goes 1, 2, 4 dropping. That's all. It's every 2 clock cycles it changes. And that's why I tried to emphasize this slight delay, right? Is because if you didn't draw the slight delay, it gets really hard to tell what the inputs are when this rising edge happens. Number 16. Where made the biggest point loss on this one was the lack of the active high reset. You guys just forgot to draw it. The other one that you missed is its synchronous counter. So it needs some combinational logic that doesn't cascade strictly through the flip-flops, right? It needs the AND gates. And again, that was just straight out of class notes. It wasn't supposed to be tricky. On the next one, the D flip-flop, when you want well, I can actually just use this guy. When you want a parallel load, it just takes a mux, right? In this case, it would be not load, it's an inverted, right? Because if load is 0, if I select 0, I'm parallel load. Otherwise, I'll take the input. And then you string those together in a shift register. And then the other part of that is make sure the contents of the shift register change from 101 to 011. Now, there's 2 ways that you could have done this. No one did the first way, which is good, which is you could have just, on the first flip-flop, you could have like drawn another shift register that had the correct contents in it and shifted it in. The right way is at the end of the shift register, you just tie it back around to the input, right? So it becomes a barrel shifter that we like to talk about. All right, number 18. I believe I put 7 errors in here and asked for 5. The first error is on line number 4. Missing parentheses. Line number 5, it says end component. It should say end outer sub. Line number 17 is missing a semicolon. Line number 30, there's a lot going on here. I misspelled bitwise. Then inside the port map, I'm missing a comma after the sum, and sum is not declared. So I would have asked you to declare sum. And then line 35 just says end, it should say end behavioral, right? Line number 29 is not a syntax error. It will give you a warning, it will not give you an error, right? So that was kind of the one difficulty in this whole thing. The biggest issue I think people have is falling for that, which sorry, and to not correcting it, right? I said find and fix. At least I hope I did. Find and correct, I did, okay. Otherwise I'd feel really bad for marking you down. Number 10, you guys rocked it. The biggest issue was not labeling the connective signals or ports that were the output of add and sub into the box. Other than that, you guys did really well. And I just wanted to help you guys make sure that you could visualize what the system looked like, because that's really helpful. Any questions on that? And if you have questions that are more personal that you want to find me in office hours, it's right after this, you can come talk. But again, overall, really well. You guys' overall grades in the class are really good. The homeworks, I haven't got graded, I'm sorry. They're basically go and give you full points for finishing them, for doing them, because the homeworks are more for you anyways. And I post the answers so that you don't leave you in the dark. I wouldn't want to do that. So I'll get those posted. Your grades will be reflected pretty accurately just by whatever your current grades are, which are overall pretty good. So congratulations, guys. I know this has been a hard semester with the masks and the COVID and everything else going on, but it looks like we'll be back to normal in the fall semester. It looks like. So there's that to look forward to.
We're looking like 100% normal.
I think so. I already got my vaccine. I'm good to go. I recommend doing the same. It's nice, and it's good for everyone around you that can't get it. But all right. Any other questions? Yeah.
So the instructions said draw an owl 6 points.
Yes.
I create this. That.
What do you mean?
It's out of 100 points. 17 breaks it down to 83 plus 6.
Oh no, that's part of the 6. That's part of the 100.
Oh,
yeah, that is a.
Okay.
Yeah, it's not 6 extra credit points. It's no. Yeah, the reason I do these, I do them a lot in most of my exams. So if you have a 3610, keep an eye out for them. Is because when I first started teaching back before I was here, even I kept having the biggest complaint that I have was from people not following instructions, and they tried to blame me for it. So I just started hiding stupid easy points in the instructions. And when it came to me, I can just look at it and go, well, you didn't read the instructions. That's all it's for. It's supposed to be easy points.
I was assuming.
Yeah. Yeah, no, sorry.
Okay.
Yeah. Yeah. So there are 94 points worth of questions in here and 6 points worth of owl.
I just assumed you.
You had the coolest
test,
owl
like, oh, I'm like, just making sure. Well, I guess
Mine
I'll
was
just
not
have
good.
an hour.
It kind of happens that way.
I was like,
The value ties to however many points I need extra. How was the timing on this one?
You labeled it owl.
I had a lot of time.
Hey, yours is good.
I actually,
Yours is good.
on the last test, I didn't get to the very last question.
Why you labeled it owl?
Okay, good. Yeah, so I like a little bit of a time crunch, but I don't want you guys to like lose hair over it. So I think this one went better. In that vein, there's an extra credit homework assignment posted right now that you guys can go online and fill out the course evals. and then just post when you finish them, my understanding is it pops up on the screen saying something like, thank you for doing this. Just screen capture that and submit that assignment. I think it's like 20 points or something. I'll give you that extra credit because I am trying to make these classes better. And it's good for you too if you have like constructive feedback, because I also will implement the kind of like conceptually into the 3610, which will probably end up taking for me anyways. So you guys' input is valuable to me. I do try and make this class easier, understandable, and a big part of this is I'm trying to make sure that when you guys get out, you can go get that cool job, right, that I posted in the announcements. So I want to make sure that you're qualified for that, but I also don't want to make this too miserable. So those course evals are helpful in me refining these courses. Okay. If there's no other questions, I mean, you can hang out. I'll be here and then I'll be in my office hours. I'll let you guys go early. It's about 20 minutes early. Use that time to work on project 2 or the lab, whatever you need to. This hands-on stuff is really important for the learning of this.
We can keep these, right?
Absolutely, yeah. Your grades should be uploaded with everyone except for Scott, who I have to do today. Great.
All right, you have mics.